Hi everyone. This series of videos is going to take you through lesson 9K in the packet, which is really an attempt to try to look at the bigger picture of logs and what they actually do for us as mathematicians. I should also make the disclaimer before we start that this is a slightly more advanced lesson in logs, and it's really meant for those of us who are going on to math analysis. In math analysis, they're going to focus a lot on logs, why we use them, what exactly they accomplish, and the big picture stuff. So if you're not going in that direction, this might not be a very useful lesson for you. It's not really like any of these problems are going to be on the final exam, and I don't necessarily think you need them in order to be successful, even if you end up coming back to math later on, like in college or something like that. So I want you to use your best judgment here. At this point, you probably can tell that if you miss an assignment, it's not like a huge deal breaker. So if you skip this one in favor of moving on to Thursday's lesson and Thursday's quick check, I don't think it will hold you back in the long run. And if at this point you're kind of prioritizing your time, I don't know that this lesson is super essential for those of us who are feeling a bit of a time crunch and just need to focus on the essential information right now. So use your best judgment, use your own personal situation and how much further in math you see yourself going as your guide to determine whether or not you really need to focus on this lesson or whether you can afford to skip it. That said, I'm still going to go through each question as if those of us who are going to do them need to know this information. So just use your best judgment. If you want to skip this playlist and skip this quick check, then go for it. And if you feel like you need it, if you feel like you want to learn it, then stay tuned. In the first video, we're going to talk about question number 1. In question number 1, we're going to revisit an equation that we explored in a previous lesson. Now, if you actually looked at that previous lesson, you may have noticed that 9G was our introduction to logs. That was something that we did in a previous week, and it was the first time we ever saw a log. We actually looked at the first problem before we did anything with the word log, and it was to introduce us to the idea that this graph, this pink thing, that we now know represents a log, is actually just the inverse of an exponential. We didn't know it was called a log at the time. We didn't really know what it was doing, but now we hopefully have put together the pieces enough to recognize that a log is simply the inverse of an exponential. So log is the inverse of exponential, just as exponential is the inverse of logs. Sometimes the word inverse doesn't really click, so I like to sometimes use the word opposite to describe what's going on here, because an inverse is just an opposite of something. So think about what you've learned in algebra so far about opposites. We know that the opposite of adding is subtracting. We know that the opposite of multiplying is dividing. We know that the opposite of squaring something is square rooting something. So we have lots of opposites that we know. And now we know that when we have something exponential, its opposite is a log. I know it looks a little weird to have words here where the rest of these things have symbols, but think of log as a symbol. It's like plus or minus. Log is a verb. It's a thing we do. We add, we subtract, we multiply, we divide, we square root, we exponentiate, and we log things. These are all verbs that we do in algebra. So think of log not as a noun, but as a verb, a thing that we'll do to problems that require it. Specifically, every problem that involves exponentiating something will be log problems in disguise. Just like when you want to add something, to get rid of it, you subtract it. When you want to multiply something, to get rid of it, you divide it. So when you exponentiate something, to get rid of it, you'll log it. And I know that sounds strange, but bear with me and this is how it'll make sense. In letter B, it says write an equation that represents the inverse of y equals 2 to the power of x. Now the best way to think about inverse is to try to recap where we've learned this before. That was way back in Unit 6. If you don't have your Unit 6 packet anymore, here's a quick little rundown of what we did in Unit 6 when we did inverses. The main idea in Unit 6 that we described was to do inverses by switching the letter x and the letter y in a problem. So if I want the inverse of y equals 2 to the x, I'll switch the letters x and y, so it says x equals 2 to the power of y instead. Notice the y became an x and the x became a y. That's what we mean by switch. Now, once you switch x and y, that's kind of like step 1. Step 2 is to get y by itself. That was what we did way, way back in Unit 6, so way back at the beginning of the semester when we were learning inverses. Now to get y by itself, this is where my previous comments are going to come into play. Because notice what's happening to y. Y is being exponentiated. That means it's part of an exponential expression. The only way to get rid of the 2 is to get rid of this exponential. Notice the 2 is not multiplying the y, so I can't divide it. The 2 is not adding the y, so I can't subtract it. It's not squaring the y, so I can't square root it. It's exponentiating the y. It's pushing the y up as a power. So the only way to get rid of something exponential is to use a log. So what I'm going to do is rewrite this problem with a log. Now if you've learned logs up to this point and feel pretty confident, then hopefully you know how to make this log structure work. I need it so that I have a log base something raised to a power that equals the thing in the middle. So let's look at this expression. It looks like the base of the log is 2 because the base of the log is always the base of the exponential. So 2 to the power of, it looks like the power was y, so the y goes over there, equals the thing left over, which would be the x. So now I'm looking at this and I'll rewrite it just to make sure. 2 to the power of y equals x. Yep, makes sense. That's what I had. 2 to the power of y equals x. It's backwards, but same thing. And now I know that I must be done. I've gotten my y by itself. It didn't look like it, but y is really by itself. That was actually what I wanted. So the inverse equation is y equals log base 2 of x. That does kind of make sense, because if I had an exponential expression with base 2, the inverse is a log expression with base 2. They kind of naturally go together. If you had 3 to the x, its inverse would be log base 3. If you had 10 to the power of x, its inverse would be log base 10. So you can kind of think about these two things as complementary. An exponential problem has a log inverse, and a log problem has an exponential inverse. So now that you've seen that exponentials and logs are inverses of each other, stay tuned for the next video where we're going to start to just get a little bit more advanced in our techniques.